Number 3, fluid saturation. Fluid saturation can vary due to the way hydrocarbons displace the seawater that was present when the rock was formed. We speak of this displacement in terms of saturation percentages, water percent, oil percent, or gas percent. Let me explain. Let's say that in your reservoir rock you have a porosity of 25%. Within that 25% you have a fluid. If you took an actual measurement of some fluid from the reservoir, you might have a water saturation of 30%, an oil saturation of 50%, and a gas saturation of 20%. This is all within your total fluid saturation. Therefore, we can write SW plus SO plus SG equals 30% plus 50% plus 20% equals 100%. These percentages are of great importance to the reservoir engineer because they give a measure of the economic value of the reservoir. Formations with high SO and or high SG may indicate a profitable reservoir. And finally, number 4, relative permeability. When you mix oil, water, and gas in a reservoir rock, they remain in separate phases and will flow through the reservoir channels at different rates. For example, if oil saturation is small, the oil will form discrete oil drops due to its surface tension, and they will not be continuously connected to other drops, and so the oil will not flow. The water molecules are continuous and will flow freely, bypassing the oil and thus producing only water. Now, if we have the reverse, that is to say, the fluid in the reservoir is mostly oil, then the oil phase is said to be continuous and it will flow, bypassing the water. The small amounts of water is bound to the sand grains by capillary forces and is said to be immovable. Thus, this reservoir would produce 100% oil. A general rule for many reservoirs is when SW is less than 25%, only oil will flow, and when SO is less than 25%, only water will flow. And both oil and water will flow when both SW and SO are greater than 25%. The next section we're going to look at the migration of petroleum. Migration is the movement of oil from its source rock, or where it was created, up in through the reservoir rock and up until it gets trapped. A trap is a hard type of rock that stops the flow of oil upward. And at that point, the oil starts to accumulate. And that's where the petroleum engineer and the exploration are looking for. They're looking for traps because that's where they find the accumulation of oil. The place where oil is first formed is called the source rock, usually a shale rock enriched with dead organic material. Once the oil is made in the source rock, where does it go? Petroleum must migrate and be trapped before it is exploitable, before we can economically get it out of the ground. Oil can migrate up vertically over geological time. Oil will migrate upward until it is stopped or trapped by rock that is hard. This hard rock, or impermeable rock, will not allow the oil to migrate upwards further. We call this impermeable rock a trap. A trap must be made of impermeable rock. It must be above, then all around the oil. It must keep the oil from migrating. There are 3 types of traps we're going to discuss: structural, stratigraphic, and combination of structural and stratigraphic. Let's backtrack just a little. Here is our source rock, laid down as deposition at the bottom of the ocean, and it got lithified, which removed most of the water, but of course some water still remains. The source rock contains the remains of the animals and plants that died millions of years ago, but it also contains some water. Now, this source rock is usually buried very deep and is under pressure with layer upon layer of newer sediment that has been laid down during the years after. This weight and pressure, called overburden, starts to chemically change the remains of these plants and animals and transforms them into drops of hydrocarbon. As these drops are formed, they begin to move upward out of the source rock into the water, which moves it further up. This is called vertical migration. Here is the reenactment. You can see how drops of oil form and then push upward, caused by buoyancy pressure or density differences between oil and water. Now, getting back to our animation, the oil migrates or travels upward through permeable reservoir rock until it disappears into the surface. Or it finds a reservoir rock with pores, porosity, and is trapped by an impermeable trap or cap rock. These drops of hydrocarbon can travel over long distances in geological time as it migrates always upward or sideways horizontally through pores and permeable reservoir rock. So when we find reservoir rock full of hydrocarbons, it does not mean necessarily that the source rock is nearby. The trap in this animation is an anticline. Here is another example. All of this migration could have taken place millions of years ago. In this structure, called an anticline, we have three fluids: water, oil, and gas. And if you remember from your chemistry, oil, gas, and water do not mix. This is because of their densities are different. If you look here where they separate, you can see a line. This is called the gas-oil contact line, or GOC. And the oil-water contact we call OWC. These lines are important for the petroleum engineer when he makes his analysis because they will determine how well the oil will flow and also how to prevent or reduce water from flowing into the well. Another thing a trap must have is closure. There must be a complete closure to make sure the oil does not migrate around it. Here is an example of a partial trap. It looks like an anticline, but it has no closure. The hydrocarbon drops can easily migrate out the back and are lost. The best traps are shaped like a bowl that keeps the hydrocarbons trapped inside. There are three types of traps. Here we will talk about the most common ones: the structural, the stratigraphic, and the combination of structural and stratigraphic. Structural traps are caused by deformation. Something big, like an earthquake or moving plates, have changed the rocks. Stratigraphic traps are caused by irregularities in the deposition of the layers when they were laid down. Combination traps, commonly known as angular unconformity traps, are composed of rock formations created from both deformation and deposition. In structural fault traps, the formation of the rock has changed. You can see where the original reservoir rock was, but the earthquake tilted the formation, creating a trap. Later, oil and gas migrated into this space and was trapped there. Here is another type. Let me tell you how it was formed first. Salt is an evaporate that is formed when the ocean water covering it dries up. This exposed salt, in time, then gets buried by other particles. As it gets pushed down and squeezed, this salt becomes hot and molten. Sometimes this molten salt pushes up and breaks the formation above it, forming a salt dome. It is structural because it pushed up and broke the formation. Some of the broken rocks are reservoir rocks, and the migration of oil will find these traps. Salt is impermeable. Whenever we find salt domes, we look for oil around them because they are excellent traps for oil.